All right. Well, I just want to welcome everybody here tonight. A quick reminder to those of you who are here or watching online, you can use the same link and token to get in that you got in last night. We had a little bit of a mix-up the night before when we ended the session, so I'm just making you aware of that. I had a few questions about it. Of course, if you're here, you figured that out. Other than that, I'd love to see comments and feedback in the forum. And just another reminder that we are doing this next week as well on the same schedule. So we're looking forward to seeing you then. And lastly, if you're having any problems, just let us know in the forum over that. Our first speaker tonight is Ken. He's going to be talking to us about object-oriented JavaScript and Canvas. It should be really fun and really interesting. So we'll let Ken take it away.
Hey, thanks a lot. So there's so much I could cover, but we're going to try to make it fit into this time and have questions and answers afterwards. So one thing I wanted to point out is JavaScript is many things to many people, and you go to Wiki, you find out about JavaScript because that's where you find everything out, right? But it points out that it actually has a mix of features that makes it a multi-paradigm language supporting object-oriented, imperative, and functional programming styles. And there's a lot of people who are using JavaScript just to manipulate a DOM or just throw a few functions together. But we had the opportunity to build some systems where you need some pretty good models of what you're building, and found that using object-oriented JavaScript is actually pretty powerful. And that's mostly what I'm going to talk about, using one of the latest things we've done as a basic running example. The URL down here, if you haven't been there, there's a Mozilla page, Intro to Object-Oriented JavaScript. There we go. Somebody's having a problem with my audio. Is there something else that needs to be done, Chuck, before we go any further?
I can hear you, but you're a little bit quiet.
Okay. Not sure what else to do here.
Where's your microphone situated?
On my computer, right in front of me. Let's see if we can change some. There's some settings here.
That, or if you have some way of getting a microphone closer to your face.
Right. Well, that's going to be harder in short order. I thought everything was good here. So
let me see if there's an option here.
Boost sound.
For me to turn you up or something.
How about that? Is that better?
Oh, that's better. That's much better.
Like better for everybody else out there?
Yep.
All right, good. Sorry for that interruption. So anyway, so this is just a bit.ly link to the Mozilla page, which is an intro to object-oriented JavaScript. If you haven't done any object-oriented JavaScript, it's a good place to start. And mentioned object-oriented JavaScript and Canvas. So I'm not going to get into a lot of the details of Canvas, but we are certainly going to be using that and showing you how you actually can test things on Canvas if you do it in an object-oriented way. So the Canvas element is out there. A lot of people are sitting on top of Canvas. It's been out there for a long time, but there's a lot of other frameworks that kind of hide Canvas from you. And we're not going to talk about those frameworks. Again, I'm just going to give you an overview of how we use object-oriented JavaScript on top of Canvas and do some pretty cool stuff. And the title of this talk was HotDraw Revisited. Now, HotDraw came from, I guess, the mother of all object-oriented languages, Smalltalk. And there are a couple, what I call my friends, the reflective practitioners, Ward Cunningham and Kent Beck. And they had the privilege of working at a research lab where they were given a lot of freedom for a while back at Tektronix in the 80s. And they would have times where they'd have a week where they didn't really have anything that they had to do. So they would take a week and say, what are we going to do this week? And one week they decided that MacDraw had just come out. And they said, yeah, I wonder what it would take to build something like that in Smalltalk. They spent a few days building it. And they just thought it was really hot. So they called it HotDraw. And it kind of became a legend. So Ward Cunningham joined Knowledge Systems for a little while in the late 80s where I was working. And Ward implemented it again at KSC, and then myself and several others extended it. Various people did it in Smalltalk. There's the years, a lot of different people have just said, hey, let's rebuild this. And did it in Java. You know, when I started doing Java in the late 90s, I built a couple versions of that in Java. And other languages have done it too. And you can, search around for different people who've done things based on HotDraw. But I'm going to kind of talk about the good, the bad, and the ugly of something like HotDraw. HotDraw was and is a simple, powerful drawing framework. Since then, there are many other frameworks and libraries for drawing, and one might say, so why not just use them if you have to do anything with drawing? And the reason I would say is that there's lots of applications for direct manipulation of drawings that have nothing to do with drawing. And I'm going to give you some examples of that. So how does one apply direct manipulation of drawings to another underlying domain and test it? And we've had a couple opportunities. A few years ago, we had the opportunity to work with the Friday Institute of Educational Innovation. We're not going to show the video tonight due to time, but what they did was they're building learning trajectories and trying to figure out how to, well, they kind of know in general how kids learn mathematical concepts, and wanted to have an interactive framework using network devices that they could kind of test the kids out and their understanding. And then we decided, at that time, we had to be on mobile devices and a few other things. And decided that what we needed to do was build it in Canvas. They had a certain look and feel they wanted, and to kind of be cartoonish for the kids to engage them. And we also found out that when you're manipulating small objects with your fingers, even with little fingers like those guys had, you really had to be careful about a variety of things. And so we built it using kind of the first version of implementing HotDraw in JavaScript. And but we learned a few things over the years. I said I've implemented HotDraw a few times, and almost every time it's not been just to show, hey, here's a drawing tool, but to do something that allows people to directly manipulate objects. So as you can see here, just a little bit larger, this is a kid. He actually had to figure out how to turn a circle into 6 parts, 5 equal parts. He was having troubles with it, in this particular child. But just by drawing lines through a circle and trying to figure out how to turn that into 5 equal parts. And there was a lot of other things we did with them. But I want to spend a little bit more time on something I've been doing more recently, which has kind of been our second implementation of HotDraw. And this is a project we're doing for Dex.com. It's actually going to beta next week. But it's a deck designer. And let me switch over to show some live stuff rather than just these static pictures here. So when you come to the deck designer, you start out with, you just figure out most people building decks have a house and a deck they want to attach to it. But we allow them to take that deck and move it around, make it larger, and actually, because this is not just a deck designer to see what it looks like, it's to actually build it. It's for do-it-yourself, or do things like take off the decking. and you can see that there's actually joists in there, and as you move it around, you can see those joists. You might see that, oh, because we got a little bit longer, we're not going to get lumber that can span that whole direction, so he realizes they need more lumber. And if I go a little further, he needs some more supports, so suddenly the beams show up in the middle. We can do some other things. Let me put the decking back on to look more like a deck. Like take an octagonal figure and maybe make that a little larger and decide that we want to place that off the side of the deck, but maybe have it go down a few layers and hook a stair to it. So we take that stair and stick it over here, and might decide, I don't want it like that. I actually want the octagon integrated with my deck, so let me move the stair over here to get to the ground and move that deck over here. It'll snap right on, and of course now it's at a different level, so we'll need to put some stairs on here. And it's not the prettiest deck, but let me raise this up a notch or two so the stairs don't go so far. A little nicer. And you say, okay, that's a nice deck. I wonder what it really looks like. And you just switch that over to the 3D view, and you can get a view of that. Whoops. There we go. So, and of course we can get the front view and side views. And all of that was just direct manipulation, and we can show dimensions on here if you want to. And notice as we have the dimensions, we move things around and everything moves with it, or the things that are supposed to move with it at least. And a little bit more going on if actually these stairs are going the opposite direction. It's not going to show up. Let me change this a little bit and make the octagon go upward. And put some stairs on here again. And as I decide I might want to shorten my deck, I get a little alert here telling me there's not 3 feet of clearance at the bottom of the stairs, which is against building code. And then you can do things like download a permit plan and a materials list and all that kind of stuff. And I don't want to spend too much time demoing that. I want to talk about how we built it. So let's see if we can get back to the presentation. So you can see a couple screenshots, change the decking, all the stuff I just did here. Showed you the 3D. And then we actually can just say download the permit plan so you can get a permit ready plan. So if anybody out there wants to design a deck and get a permit ready plan in a few minutes, wait for the next few months when it goes live. But say to get a materials list, etc. But let's talk about how we did this and kind of the concepts behind HotDraw and how we applied this and how you can use these same principles to do something that you might want to do that's directly manipulable rather than your typical crud of putting in your data and hoping that something good comes out the other side. So HotDraw, Ward on his wiki described HotDraw, and it's still out there if you want to go out there and listen to his, actually the initial CRC cards. I don't know if people have ever used CRC cards. Class responsibility collaborator cards. He drew these cards up to describe what was going on. So as he described HotDraw, he said, we started out with the usual model, view, and controller. And the way we implemented these in JavaScript, and these are way simplified versions of what we've got, just trying to get the gist of it. The idea of a drawing, that you can add and remove figures from them, and you can draw those figures. The view, oops, use the mouse. Okay, there we go. I'm sorry, I skipped forward a little bit too far. So use my there we go. So the view is really just a canvas, right? However you're going to do your HTML view. We use Jade in this case, but just have a canvas, and that's what you're drawing on. That's your view. And then when you go to your controller, we just did a very simple thing. We created a drawing controller. You give it a drawing and you give it a canvas, and we'll come back to the initialized mouse observers in a few minutes. But basically, you tell the drawing controller, you say draw, and it tells it basically tells its drawing to draw on top of a context, and we'll show you how that works in a minute. So after looking at the basic model view controller, he points out that the drawings, the main model in HotDraw, drawings hold figures. And he drew the idea of an abstract class of figure with a few refinements. And we found over the years that instead of just calling things figures, start with a drawable. Because if you're just drawing figures, that's great. But if you have something else that isn't a figure that has some other semantic meaning, we just want to have something that knows how to draw. And so we came up with this drawable, and all he does is have a few properties, and he's kind of our abstract class, so that before you draw anything, it sets the context, sets the properties on the context, and draws it. But you can do something as simple like a polygon figure, give it a few vertices. You'll see here that we created a class called a polygon, and you tell the polygon figure to draw itself, and he just does the right calls on canvas context to draw that. So the other thing Ward points out is drawing controllers collaborate with tools to make changes. Now, he said he didn't make a card for an abstract tool, but we found out that we needed an abstract tool, so we built one. And the basic idea of the tool is it knows about its controller. He can get to his drawing through the controller. When the tool activates, he keeps track of what was the previous tool on the controller, so he can set it back. And notice here in our tool we have draw, and we also have mouse down, mouse move, and mouse up, and the default does absolutely nothing. But when you get a selection tool, it gets a little more exciting. Selection tool actually has a group of handles, and he'll figure out what got selected based on something like putting a mouse down. And he would find out the handles and then do the right thing, passing onto the handles, because all we really do in the controller, when mouse down, mouse move, mouse up, or whatever like that happens, he just passes that onto the tool. And the tool himself may end up passing those things onto handles. And so, we have an abstract handle. It understands things like move from, to, and draw, and we made lots of different kinds of handles. And actually, one of the most interesting tidbits that Ward wrote in his initial HotDraw design was, finally, locator is a point substitute that knows how to propagate changes between related figures. For example, when a line connects to the corner of a box figure, and the box figure moves, an updated message propagates through a locator to the line. Now, it's interesting, if you read further on that, Ward says, actually, we didn't actually use locator in the initial HotDraw. But we found that it's a pretty powerful point, and there was a pun intended there. So a key point is that, geometry is the foundation of many domains, and a point in common with drawings of all sorts. And it's also the connection to many black boxes. For example, browser events, right? They'll give you X and Y coordinates. If you get gestures or anything else, you'll have those things. And what I would argue is they're really the things to test, not what's actually showing up on the screen. If you've ever tried to test something that's on a screen, you've found that it's kind of hard to do that usually, because what's going on the screen is usually in a black box. So what does this all have to do with objects and Canvas? Well, there's a couple of things that I think are really important if you're doing object-oriented JavaScript or object-oriented anything. Two really powerful tools I found over the years are self-encapsulation and lazy initialization. And let me talk about that a little bit. So suppose we have a point, and in the geometry space that we all learned in school, x goes to right and y goes bottom to top, but because we're computer scientists now, y goes down. But either way, it's still the same concept. Am I seeing there's somebody who has a feed broken? Are we good to go? I'm going to continue unless somebody breaks in and stops me. Okay, everything's good. All right, so we have a point, and the naive user might just say, we want an object in JavaScript. We just do something like that. We create a variable p and give it properties x and y. And after all, we can use that to draw an arc or a circle in this case, and we can draw that on a canvas. And that's all we need. But if you think about the geometry behind here, you might want to approach it a little bit differently. We actually created a point or a class or a prototype called point. And then you do things like draw it this way, but instead of using the property x and y, we made a function call. I know that there's a defined property in some versions of JavaScript. We found that that's actually a little bit slower than what we want. At least it has been. Things might have changed yesterday as things change, but the idea of sending a message is kind of fundamental to object. Way back when Smalltalk did objects, we'd send messages. We didn't call functions, but it's equivalent basically. So notice that by sending x and y, or treating x and y as functions, what you can get. We have encapsulation of a point, and you look at this and say, well, there's no real benefit to that. We know there's an x and y. Why not just refer to them directly as properties? Well, that's exposing the inners of the object, and as soon as you start doing that, especially in JavaScript, you have to go back, and if you ever change your mind later, you got to change all your properties to function calls, which can be done. But usually it doesn't have to last too long till you realize you might benefit from that. So for example, if you wanted to have a polar coordinate, which comes in handy when you're doing certain things, and you can use x and y there also, and you don't have to care whether you have a point or whether you have a polar coordinate. You just ask for x and y, and then you can do other things. We also found there's lots of other ways to get things besides just the simple points. Here's an example of an edge relative locator. Give it an edge, a point from two locators, one locator to another locator, and you give it a distance, and then you can ask for x or y by just asking for x or y, and it can calculate how far along that edge that locator is. Or you can decide that that function is a little bit expensive, so you use lazy initialization to return the last x we calculated unless x has been wiped out based on some other event. So by doing that, you actually get a lot of power. So there's lots of ways you could do this. We have our own implementation. But basically, you make a locator class or prototype with all the methods you'd want a locator to have, x, y, and maybe some other things. make it the prototype for all the specific types of locators, and always refer to the properties by calling functions or sending messages. We even do it internally to the object, calling self-encapsulation. And then you can do things like add two locators together. And you can either add them by saying, okay, well, assume when I add two things, I get a point. Or you can say, I don't really care what I get as long as I understand X and Y. So you could just return a function if you wanted to. Again, we don't really care, but the point is that lots of locators can be very beneficial. And here's some of the locators we've come up with in order to build the deck designer. An edge intersection locator, edge relative locators, both fixed distance from an edge, and whoa, what just happened there? Somehow my jumped way back. And let's catch up a little bit here. Okay. So, yeah, so fixed edge locators, proportional edge locators, so something that's halfway down the edge. A normal to edge locator that says, okay, somewhere along the edge to a certain point and offset by a certain amount in the normal direction. Polar coordinates, relative locators. We got into 3D locators. So you can take an XY position and add some relative Z to it. Or you can have a XYZ locator and you only care about X and Y, or you only care about X and Z, you only care about Y and Z. Or even a three-source relative locator that gets X from one place, Y from another place, and Z from another place. And using this, okay, sorry about that. Using this, we can actually get some pretty powerful stuff. And in this, we also came up with geometric models in addition to locators, an edge, a relative edge, something that's some subset of another edge, polygons, rectangles, circles, and then we added some 3D things, cubes, extruded polygons, and a triangle mesh to actually do a lot of the math that's needed to display it. So key point is, the geometry is something that matters to the domain model, and the geometry at some level is what you're rendering. In fact, if you look at just about everything on the deck designer, almost everything on there is a polygon, little bit of text, a few lines, and a couple circles when you get to footings, which I didn't really spend any time showing you. But the figures is what you render on the screen on the canvas. So these things know how to display those figures. But the geometry is really used elsewhere. So as I showed here, we have a closed shape figure that is an abstract class for some other things like a polygon figure and a circle figure that you can do things like move it. You can ask if it contains certain things. You can ask it for handles, and of course you can draw, and the subclasses would do that work, and that's just really a matter of simply figuring out which call you have to make on the canvas context to draw the right thing. So as I point out that the geometry is what we're rendering, we actually added a few methods to standard context, so we can do things like tell it just to draw a circle. You don't have to do that. Don't try this at home. We're trained professionals. So the geometry is what you're rendering, but it's also our domain model using the geometry. So our deck frames are basically all derived from some number of locators. And those locators might be relative to some other reference locator, for example, the corner of a house. It could be the corner of another deck. And we also use things like material specs for our deck frame to tell us what kind of material to use. And actually that material also supplies some dimensions. For example, we're using 2x10 versus a 2x8 for a frame. And the joists and the boards and the posts and all of these things can be placed by simple formulas, locators, and material specs. So let's put all this together. How that kind of comes together. So this is a Jasmine test. All of the entire system is all test driven. And I'm just describing a rectangle deck attached to a house. So if we look at what we're doing here, really simply, we create a new deck. We create a house, a rectangular house frame. And tell it we're picking 480 by 300. This is in inches. We could use other units. That's what we chose. And a rectangular house frame basically just takes that width and length and assumes a reference point of 0, 0, that your world is going to be in reference to the corner of the house. So he creates a few locators. Starts out with a reference point being a relative locator, and we could later change that reference point to something else if we wanted to, which is so why we start out with a relative locator on point 0, 0, 0. And then we just create 4 new locators for its vertices. And the rule for our house frame is that it goes basically north of our starting point. So we kind of go up from there. So as we draw that house, or as we're not even drawing at this point, we're just having a concept of the house. That house basically is relative to those 4 locators. It has those properties. It can have other properties too. It does have other properties, but we're only going to focus on that right now. So we add that house to our deck, and then we create another rectangular deck frame. And a rectangular deck frame, we chose to make the frames go south of 0. So I gave it those 2 dimensions and does a very similar thing, but he just draws in the opposite direction. And then we can do something like move him by 24 in the x direction and 0 in the y direction. And when we do that, of course, he just does a couple things here, like tells his reference point to move. And when he told his reference point to move, everything else moved. That was just on the relative locator to move his x, y, and z. And since all of the other locators were relative to him, he just moves. So now we have our rectangle moved over there. And now I tell the rectangle to check attachments. This gets a little hairier. But when we check those attachments, we're leaving a bunch of code out here, but he says, okay, what are the target attachments? Based on the location, he finds out what else is there. And he happens to find out that, oh, this deck happens to be at the edge of the deck happens to be at the edge of a house. So that gives us a deck to house edge attachment. And that deck to house edge attachment does something to figure out where his relative locators are. And he knows that because of where he is, that he's going to, because he's going horizontal rather than vertical, he's setting up his proper X and Y sources for his new location. So now all of a sudden we expect that after you do that, that your deck is actually attached to your house, and we want to then check, did that actually happen? So I now take my house, I record where my rectangle's box was. I now move one of the house's edges by 10, and hopefully the rectangle, the frame moved also. And our test pass, and it does. And we see that a few things have changed. Now, notice when we did that, moving the edge, we actually changed some of the relative locators of the house. Everything else moved, and it all works. So the cool thing is we can build our domain, test all this stuff, all with geometry, has nothing to do with seeing anything on the screen. And we can make sure that everything works. So how does that map to actually rendering it on the screen? Well, this is where we get back, and we have a deck view controller, and we'll jump into that in a second. So we look at our deck view controller, and I think earlier we said our controller takes our drawing controller took a drawing in a canvas. Our deck view controller is not much more than that, but he happens to hold on to the deck also. It's convenient for other reasons. So we give it a deck, a drawing, and a canvas. And we get our drawing by asking our deck for its top view. And he just gives me a new deck drawing on the deck. And the deck drawing isn't really complicated. He just asks each of his components of his deck. He sorts them by their Z level, so the things on top show up on top, and gets a figure for each of those. And the deck view controller just subclasses our drawing controller, and that's our starting point. So how does that actually work? Well, our deck view controller on load goes out there and looks for an element by ID top view, and then he says, oh, if I get one of those, then I'll use that canvas. I can go out and build my house the same way I've been building it and tell the controller, here's your top view, which is a drawing, and here's your canvas, which is what you're going to draw on, and I can tell the controller to draw. So a really interesting thing that's happening here is, again, the canvas is just an element that allows you to draw on it, and it's really hard to test. What did I just draw on that thing? But our drawing ourself, our model, holds the figures, and our controller captures events and manipulates the view, or does it? Let's look at the piece I didn't show you earlier. Initialize mouse observers on the drawing controller just gets the canvas and says, okay, I want to start listening for certain events. And he maps those events to mouse down, and if you scroll down further, which we're not going to, mouse up, mouse move, whatever, and just passes that on. So the interesting thing is, drawing controller, if you have no canvas, you don't initialize any mouse observers, and drawing never happens. So you can test everything besides these two things. Once you've figured out how to get your mouse observers working, and the fact that the drawing controller is just telling all the figures to draw themselves, you can test everything else you want. So really, what we're dealing with here is we're just manipulating the drawings and the figures and or the underlying model. And we're really not manipulating a canvas at all. The canvas is just a place we're painting the result on. So we can test our result before we paint it. And the event observers strip out the position. So we can also do things like test the controllers, the tools, and the handle, right? Simply create a controller outside of any HTML element, test what happens when you send those pseudo events like this. I can describe my drawing controller. I create a new drawing, I create a new controller without passing it a canvas, and I ask the controller for its active tool. And I do something like move the mouse down and see if the active tool got the mouse down. He sure did. And if my active tool is a selection tool, I can test things like that. Create a drawing, create a figure, create a test handle, create another polygon. So I got a triangle and another polygon up there. I add them both to the drawing. I set up my controller, my tool, and now I say if the tool's mouse goes down, what happens? It should select a handle, and it should be the handle that I expect it to be selecting because I put the mouse down at the point that I wanted to have happen. So I'm testing everything as if the mouse went down at a particular point, and by doing that, all I have to do is at one point in time just make sure that my mouse observers are observing the right thing, and I'm mapping my X and Y events to the proper dimensions, and I can test everything else. And do the same thing with the handles. It's all the same principle. Create a couple locators, create an edge. This is my edge handle, and I want to find out that if I tell the handle to move in a particular direction, we want to only make sure that edges move perpendicular to their orientation, and it tests, and that all works too. So that's, we're testing things like, when I go back to my desktop, that we're basically saying what happens when I move that edge. We're testing it all. We can't really test that the canvas got rendered correctly, but we can test that everything that happened was supposed to happen so that it should render the canvas correctly. So in the midst of that, I showed you the frames. When are the bands and the joists and the surface boards and all those things created? They basically only get created when we need to draw them. So most of the deck frames you see, we don't really even care about the joists and all until we need them. Or except when we need to draw them, or we need to put them in a material list, when we need to put them on a permit plan, wherever. It basically lazy initializes the figures when we're trying to draw them. And that's what I'm doing at this point in, what I just showed you was actually just making the frame and drawing it. And if it's trying to draw joists and deck boards, then it needs to create those. But I can just ask the deck frame for its bands and ask each band for its figure. Well, if that band isn't there yet, he'll get created. But I can just start changing my deck frame size and shape. I can trash my bands and then just recreate them over and start over again. So for example, here, my deck frame, I ask for bands and say if I have bands, give it to them. If I don't have bands, figure out where my edges go. Figure out what my material spec is for my bands. The bands, by the way, are the edges of the frame that hold up the deck. And then I create a new band based on where the edge begins and the edge ends and the material spec that I need. And then I give it some offsets to offset from center of where I want that band to go. So as we we'll look at that a little further, the band is just a subclass of material, and we're basically just calculating the vertices of where that band's going to go based on that. And you'll see here that everything is proportional to another locator. So a lot of the reshaping we do as we reshape the deck, if those bands are already there, they just move when the locators move automatically. And if I ever need it in 3D, I extrude it. That's what that extrusion length is, and we'll see that in a little bit. Any material can turn itself into an extruded polygon. That works for us because we're dealing with boards on deck frames, and they all happen to be extruded polygons, three-dimensional, not anything fancy, no splines or anything weird like that. But once I have that 3D figure, I can get the XC figure to see the front view or the side view. And I can get the shape in 3D if I need it. So those are all happening as needed. And if I look at this frame and see what's really going on, just kind of a little more graphical picture of what's going on. There's the frame. The frame is made up of just a few locators, and two of those locators make up an edge. And the material spec just tells me things like it's a 2x10, which has a width of 1.5 inches and a depth of 9.25 inches. And based on that, I can create 4 more locators that says where that band comes from. Like drawing from the width and the top, the fact that I'm looking at it from the top. He says, okay, that's 1.5 wide, and based on that 1.5 wide, I draw my locator off of the original locator 1.5 away, and do that at both ends. And now I've got my band, and I can do that around the rest of it. And now I get to the joists, and the joists do the same thing. They go along that edge, and they decide that they're going to put each of the ends of the joists every 16 inches right down the line, and those are all created. And as I move my corners, if I move that corner of a frame, everything else just moves with it. Right. So again, due to lazy initialization, there's no reason to ask for a 3D version at this point. I'm just trying to draw the deck. Only the X and Y vertices are really used to draw. It does ask for the Z, just to make sure he knows that a deck on top of another deck. I'm only drawing the top one, doing it in the proper order. And the Z coordinate may have been needed when we were attaching components. So trying to figure out where the stairs go and how many steps go down and all that kind of stuff. We got to figure out where the Z goes. But again, it's only using those as it needs them. Nowhere during that time did it ever need to figure out what does the 3D mesh look like. So once that material is located, it can be extruded into the 3D on demand. Any 2D perspectives, so faces of the extruded polygon, can be retrieved, so I can look at the front view, the side views, whatever. The same locators and shapes can be used to draw the perspective. So I'm looking at the same locator from the XZ view, and I have several coordinates to give you what that polygon is going to look like from that side. So I can draw it on a canvas, but because I've abstracted this, not only can I draw it on a canvas, I can draw it in PDF. We use PDF Kit, which is a brilliant JavaScript front end to PDFs. And thankfully, it used the X and Y in the same direction as our screen does, unlike PDF. Naturally, it did the inversion for us. But we can take those same locators and say, let's use those locators to draw the permit plan. And then we can do the same thing, use those same coordinates to get our 3D mesh and show it in WebGL. If we wanted to, we can convert it to SVG or any other system that happens to use geometry, right? Which is just about anything that's drawing anything anywhere. So in summary, in JavaScript, when we used an OO language, we can build pretty powerful models. I encourage you all to leverage encapsulation, leverage polymorphism, and leverage lazy initialization to do that. And if the geometric concepts are realized, the models could be rendered in many, many ways. And notice here, as I already pointed out, the DOM and the event handling can be a thin veneer so that you can test the rest. Notice I marked here that you can move the whole thing to Node and do it all on the server if you want to, which we actually are going to be doing. A lot of the rendering, the permit plans and stuff are going to happen on the server rather than on the client, for example. Same model, works in both places. So that's it for now. Chuck, I think we have about 10 minutes for questions and answers.
Yep. I'm going to go ahead and switch over to Q&A mode. That way people can ask you questions by enabling their microphones. And then while we're doing that, then we'll start asking questions out of the chat. So if you have a question, go ahead and click the Ask a Question button, and we'll get that asked. While we're waiting for people to raise their hand, Stan Fisher is asking, have you tried using WebGL instead of Canvas? If so, is it faster or slower?
So the 3D view is WebGL. So let me switch over to this. This is all WebGL over here. So we just turned our 3D models into WebGL components. So I'm not sure if it said faster or slower than what?
Probably than Canvas.
Well, I mean, WebGL is really you're just drawing WebGL on top of the canvas at the end of the day.
All right. Harold Short asks, does changing material type cause the layout to change, like spacing between joists? If so, can you show us?
Yeah, actually, in this release, we're not giving the user options on that, but they do have options on things like the footing size. I didn't show you the footings, the railing height. So if I just change that to 42 inches, and I guess you didn't see the previous versions, but those are 42-inch rails now. And did that not work in the top view? Whoa, there we go. Change that to 36 inches. Trying to change it to 36 inches. Something's locking up on me. Demo land.
Well, we'd know if your internet went out.
It worked. So yeah.
All right, the next question is, what would it take to do a section view across an arbitrary plane? It would require projection transformation of faces.
Yes. Right, so we can kind of do that. But yeah, I mean, it's really about your model and how much math you want to put into your model. But yeah, we definitely have some more complex math in certain places, and others we're just letting, like WebGL takes care of all that in the 3D space. You just tell it, here's your stuff, and as you rotate things around, rotate your camera around, it takes care of it for you. But you can do it mathematically if you wanted to.
Cool. Okay, OSM, who I'm going to pronounce as awesome, is this source available anywhere?
No, well, certainly the Dex source is not. We are planning on, at some point, taking some of the base HotDraw type of stuff, and we will make that public. We don't have a particular schedule on that right now. We're trying to get the beta out, and we've designed it such that there's a different layer for that, but we haven't spent the time to verify that and document it, and provide the nice demos and stuff you'd want to do to show that. Check back on RoleModel's GitHub account, and in a few months, and it's there.
All right. Aaron Klander says, in your opinion, what is the most challenging part of doing OO in JavaScript?
Boy. There were certainly some things that we had to get used to. Some of the way that constructors work when you start inheriting a few different layers down. Well, I mean, the functions you're inheriting prototypes, and that was probably the biggest challenge. The other is that there's no good tools that we found yet that will show you the hierarchy nicely. So there were times when we're trying to do something, and we have like an octagonal deck frame is 3 levels deep in hierarchy, and there's no good way that we found yet, and we probably haven't looked hard enough, but no good way to say, okay, this method came from 2 layers up, we just have to know the hierarchy and know where to look. So that's so really the tools will probably be the biggest challenge. So the constructor issues, we eventually figured out how to work around that after getting bit a couple times. But once you got past the constructor issues, it all works beautifully.
All right, Harold Short is asking, do you code in ES6 or something and file?
No, we did all this in straight JavaScript. We thought about CoffeeScript, and when we started this whole thing, just didn't feel like there was a compelling reason to do anything different besides JavaScript. I don't see any reason it might not work in any of those other things, but we just didn't.
Can you share some resources to learn how to start embracing the OO paradigm? That's by Federico.
Yeah. There's been a lot of good books in the past about objects. Unfortunately, once everybody started using object-oriented programming, people stopped teaching about how to do it well. Back in the late 80s and early 90s, that was all about it. It's a different paradigm in programming. And unfortunately, that didn't really make it into the schools very often. There's very few schools that I know that do a very good job of teaching object-oriented anything. There was a book by, why am I blanking out his name? Dave West, the Microsoft Press did a few years ago about object-oriented. It wasn't JavaScript, but it was an object-oriented book. And then there's a classic one by David Taylor that was written in the late 80s. In Ruby, Sandy Metz recently wrote a very good book about objects in Ruby. I haven't found a particularly great object-oriented JavaScript tag. I mean, part of it, I kind of grew up in the 80s in Smalltalk, so I don't think I have to spend a whole lot of time learning how to think object-oriented now, since I've been doing it for a long time. But those would be some of the places I would look for those books. Somebody else out there might have another good suggestion if they found a recent one that they found helpful.
Yeah, there's a link in the chat for an OOP and JavaScript book.
Yeah.
For what that's worth. It's always nice to see examples in whatever language you're actually using.
Right.
All right. Well, it looks like. Okay. Have you tried TypeScript, and what's your opinion about it?
I've heard other people talking about TypeScript, and I'm not inclined to shift TypeScript. I mean, I'm very comfortable with non-typed JavaScript, but that doesn't mean doesn't have its good uses.
All right. With this application, did you run into any issues around browser memory or performance? And if so, how did you tackle them?
Yeah, browser memory, not so much. Performance, we, using a lot of the lazy initialization techniques and then just caching, that got us the biggest performance bang for the buck. When we're calculating all those joists and everything, it started slowing down. We started building decent sized decks. Then we found just by caching those locators, a lot of it came from calculating the angles and the edge locators. And if you just cache it when you calculate it, it ends up, we got huge performance benefits from doing that. So another benefit of lazy initialization, we found out where it was spending its time on these same methods time and time again, and just said, okay, can we cache the answers and get some benefit out of that? And we tried that. It took about 3 hours one night to get a huge performance increase from that. Which is typically what I found is you make it run and then you make it right, and often you make it, if you've done a good job of encapsulating, then you just figure out where you need to do some shortcuts and do some caching. Usually in just a handful of methods.
All right. Well, it is 7 o'clock here, 9 o'clock Eastern, so we're going to end the Q&A here. Thank you, Ken. It was really interesting to watch. And, everybody in the chat, if you could give Ken a virtual round of applause. I'm going to set back to presenter mode for a minute so that Rahat can get ready to go, and then we will be back in a few minutes. Thanks, Ken.
Thank you.
It doesn't want to.